Hello everyone, my name is Arman Goshtasbi and I'm presenting our recent work on AI-infused soft fluidic tactile sensing. First, why tactile sensing, or in other words, what are the applications of touch in robotics? One of the main applications of touch in robotics is improving human-robot interaction. Similar to human and animals that uses their sense of touch to interact with the environment or interact with each other, uh, having sense of touch on robots can enhance the experience of the human-robot interaction. Another application is manipulation, that a gripper via sense of touch can detect the structure, shape, rigidity, or softness of an object and adapt to it accordingly and grasp it more efficiently. And last but not least, exploration and surface texture detection is one of the main applications of touch in robotics. Benefits of softness in tactile sensor is ensuring safety, since most of the soft robots are safe, perceiving complex structure by adapting to the complex structure, eliminating rigid electronics at the sensing site that gives us the adaptability as well as ensuring safety as well. And finally, more nature-like perception similar to the skin on human and animals. Here are a few examples of the soft tactile sensors that have been proposed so far. Numerous methods have been used, as you can see here, either using fluidic motion and capture it by camera, resistive reading, capacitive reading, pressure sensors, optical sensors. Despite the benefits of each of these works, they either require complex fabrication or they rely heavily on extensive number of physical sensors, or finally, they require electrical components at the sensing touch, which limits the applications where there are electrical interferences. Therefore, in this study, our goal is to create a simple electronic-free at sensing site soft tactile sensor. And by simple, we mean simple in design and fabrication, and electronic-free at sensing site, which means that we don't want to have any electronic where the tactile stimuli occur. Our approach to achieve both of these goals are using pressure-based sensor, and as a result of that, to enhance the performance of our pressure-based sensor, we studied the effect of fluidic properties, in this work viscosity and compressibility, on the pressure reading and the performance of the sensor. As mentioned, we were looking for a simple design, and therefore we propose a simple circular fluidic channel, 1D circular fluidic channel that deforms under the tactile stimuli and that produce two pressures at the two ends of the channel. And by reading these two pressure, we are able to detect both force and position of the applied stimuli. For the fabrication, following the simple fabrication, we simply 3D printed a mold, pass a rod through it, and we poured silicon rubber, which here is Ecoflex 30, into a mold. And after it's cured, we removed it, connected the tubes, inject a liquid in it, or keep it with air. And in this study, we studied three different mediums: air for compressible, water oil for incompressible, and also water and oil for different viscosity. Finally, we used UR robot to poke the sensor very precisely, and we collected the data using the load cell and pressure sensor and data acquisition card. Using the setup shown in the previous slide, we did some initial tests. As you can see here, we poked the sensor on 3 points: extreme left, middle, and right. And as you can see here, on the left, the pressure of the left pressure sensor is higher. The pressure reading on the left pressure sensor is higher. On the right, it's vice versa. And in the middle, they are equal. So we concluded from this initial result that the closer it is to one pressure sensor, the higher value we are reading. Moreover, by changing from air to water and oil, so from compressibility to incompressibility, you can see that the difference at the two extreme ends become more significant, and also the pressure level in general increases. Moreover, from water to oil, we can also see that the pressure level increases and the difference become more distinctive as well. In addition, we did the experiment for the different diameters. As you can see in the figure at the bottom, all of these results are for the left extreme. By increasing the diameters, the pressure reading increases, the force values decreases. But despite the pressure value increase by increasing the diameters, as you can see, for example, for diameter of 3 millimeter, for depth of 1 or 2, the pressure resolution are very low, unlike for 1 millimeter and 2 millimeter. So although the pressure increases, but there is a trade-off that for lower light touches, it might not work properly. Based on the initial result data that we got, we decided to choose 2 millimeter diameter and do extensive data collection and machine learning. We did linear data collection with the numbers that you can see here. We followed this pattern. We collected the data. We divided into trained data and test data. We applied 4 different machine learning methods: linear regression, polynomial regression, multi-layer perceptron, and support vector regression. We were able to achieve following model scores. As you can see here, we were able to achieve position resolution of 98% and higher. And as you can see, for water and oil, this result improved compared to the air. For force, however, the oil does not perform in the level of air, but water performs the best, as you can see, by 93.71%. So this result shows the water, having water is the best solution for our sensor. Therefore, we did some estimation as well. And as you can see in this figure, we did both force and position estimation, and the predicted and measured force data were close to each other by high percentages. To put the result that we got so far into the application, we were able to control a UR5 as a human robot interaction here. So we were able to, on the left side, by just controlling the position, and on the right side by controlling both positions and the intensity of the touch. To conclude this work, first, we created a simple pressure-based tactile sensor that has a high resolution, and it is suitable for robotics application due to its softness. Second, we investigate the effect of compressibility and viscosity in this study, in general fluidic properties, in the pressure reading and the sensor resolution. And finally, provided the baseline for future work on this simplistic channel soft pressure-based sensor. For the future work, we're going to extend the same principle into the 2D and 3D and benefit from the fluidic properties and read the pressure and reduce the number of physical components here. Here, I want to thank you for your attention, and also I want to thank my colleagues for the help that they gave me. And if you have any question regarding this work, don't hesitate to contact me, or you can visit our website at softwarerobotics.dk. Have a nice day.